be able to do the calculation there, but how to find the conversion factor, how to set up the dimensional analysis equations there. That's the key there, and that's why I think most of the faculty members here on this campus there, when we teach chemistry, general chem, 101, 102, that's our approach. We want to show you how to set up the equation, and so that you will be able to, given a different question there, you will be able to look at the questions given there, you will be able to know how to set up the equation, how to do the calculation. And that's the primary reason why we choose this particular textbook, because this particular textbook, the previous textbook that we used was a pretty good textbook, but the explanation of problem solving is somewhat confusing. And when we switch to this particular textbook, and you can see step by step, and those people who took the time to read the textbook, you will see examples and solving the problems step by step, and then followed by practice questions. So using this particular textbook, it definitely gives you a fairly clear approach on how you are going to approach a particular question, how you're going to set up the equation, how you're going to answer the question and get the answer. And then after going through the example in the textbook there, the author also gave you many different types of practice problems in addition to the homework assignments there. Okay, so back to the chapter 5 and gas law there, and we're talking about, we've been dealing with gas mixtures there. And one of the issues, as I told you there, is that when in the laboratory there, when you produce a gas product, then one of the challenges there is always how do you collect this gas? Because if you just let the gas evolve from the reaction, it's in the air, it's mixed with the air. So this is a setup that we can actually collect gas products. So in this case, if you have a piece of metal zinc and you have hydrochloric acid, you mix them together, hydrogen gas is being generated. So hydrogen gas is leaving the system. If you use a glass tubing, direct that hydrogen gas into water, and then you put a beaker on top of that opening of the glass tubing there. Hydrogen gas is coming out, and then the beaker is filled with water there. Hydrogen gas is coming out, and the pressure is building up, and so pushing the air, pushing the water out of the beaker there. So in the open space up there, and in the space up there inside the beaker there, and you have your hydrogen gas collected. Okay. Before the water is completely pushed out, you can always put something to cover the beaker and flip it over, and you have the hydrogen gas collected there. Of course, you can manipulate the collector that you are using here to make it easier to store hydrogen gas there. So, but the problem here really is that if you collect hydrogen gas in this manner, you are not just collecting hydrogen gas. Water in here is vaporizing. It's going to be a mixture of water vapor and hydrogen gas. So if you're trying to calculate the quantity of the hydrogen gas that you have, you're using PV equals to nRT. P would be the total pressure exerted by hydrogen gas and water vapor. Okay, so we have done enough study to figure out what we call the vapor pressure of water at different temperatures there. So the total pressure here is the sum of the water vapor pressure plus the partial pressure of hydrogen gas. Now, if you're trying to do a very accurate calculation there, the partial pressure of the hydrogen gas has to be figured out. And the total pressure we can measure, the total pressure outside equals to the total pressure inside. And that's why when the total pressure is slightly higher than the outside pressure, the water is being pushed down. Okay? By the time all the water is pushed out, the pressure inside here equals to 1 atm. But that 1 atm is the sum of water vapor pressure plus the partial pressure of hydrogen gas. So if you're only dealing with, if you have to deal with just the hydrogen gas there, you have to take care of the what we call the water vapor pressure there. So at different temperature, this is something that you can see you can find in chemical literature. And at different temperature, water has a vapor pressure in terms of millimeter mercury. Okay? So if you're doing the experiment under 25 degrees Celsius, room temperature there, then vapor pressure of water is 23.78 millimeter mercury. So the total pressure in that chamber where you have the water vapor mixed with hydrogen gas, the total pressure, say, is 760 millimeter mercury. The partial pressure of hydrogen is 760 minus 23.78. Okay? So this is using the Dalton's law of partial pressure, and this is how we take care of the water vapor pressure in the presence of a mixture when you have hydrogen gas and water vapor mixed together. So at different temperature, water has a different vapor pressure. And by the time you reach 100 degrees Celsius, water is going to be in the gas phase. Okay, so this is the situation between 0 and 100 degrees. This is the situation water can coexist in the form of gas and liquid. Okay? And when the temperature goes beyond 100 degrees or above, water is being converted into vapor, and water is a gas now. Okay? So here, everything that we have to deal with and really is partially water, partially liquid, partially gas. So we have to take care of the vapor pressure of water when you have a mixture of gases, and when you're collecting gas product over the surface of water there. So we do have some examples on page 218 in your textbook in chapter 5 there. So make sure you look at those questions there. And the homework assignments related to this particular topic is also given there. Now the thing here is that we don't give you a very specific example in class there, and we ask you to look at this particular example on page 218 in chapter 5. And make sure you take a look at it. And it's a simple addition. Okay, total pressure of the gas mixture with water is partial pressure plus the vapor pressure of water. And at different temperature, water has different vapor pressure. So if you need to figure out the partial pressure for a particular gas mixed with water vapor, and you know the total pressure subtract these numbers at different temperature there. I will give you the partial pressure. If you know the partial pressure, PV equals nRT, you can figure out the number of moles. You can figure out the volume. Okay? And going back, that's why we say the central equation that you need to memorize in this chapter is that PV equals nRT. Okay? Now, we've been dealing with ideal gas law, and the ideal gas law is based on a series of assumptions, and that we call kinetic molecular theory. And we want to take a look at those assumptions again and try to understand what's the relationship between the molar mass or the weight of the gas versus the speed or the energy carried by the gas is there. So we want to list and explain the assumptions, the postulates of the kinetic molecular theory again, and then we will give you some examples on how do we use those theory to predict the behavior of gas there. So that's our fourth learning objective there. And this particular area of chemistry is pioneered by Clausius and Rudolf Clausius. And he studied a lot of, that's the pronunciation in Chinese translated, so I put his name in there. It's a very famous physical chemist there, and he studied the behavior of the gases there. So we made a lot of postulation. And the first thing about the kinetic molecular theory is that a gas is a collection of a very large number of particles, and the particles remain in constant random motion. Okay, so this is something that you need to what's that word? Memorize. Okay. There are 6 postulations there, okay, and you need to remember these are the assumptions that we made about the gases, so that we can study the behavior of gas. So the first thing here is that gas is a large collection of large number of particles, and then those particles are always in random motion. They're moving to all directions there. And then the pressure exerted by gas is due to that random motion, collision between the particles and the container wall. Okay, so that's where the pressure comes from. And the third one says the particles are much smaller than the distance between them. So we are making the assumption if you have 2 molecules of oxygen gas and suck the air out of this room,